welcome to this online presentation. My name is David Ware and I'm here from Fire Risk Consultancy to give you an online presentation on unravelling the mystery surrounding Bernoulli's theorem. Now, this presentation has been prepared to assist those sitting the science paper of the membership examinations. What I'm going to do is dispel the mystery surrounding Bernoulli's theorem in an easily understood manner, and then to show you how to apply this to previous examinations by giving you some model answers. Now, first of all, a bit of background. Now, Daniel Bernoulli was a Dutch-born Swiss scientist who discovered basic principles of fluids. And the Bernoulli principle is that a fluid, liquid or gas, in motion can have three types of energy. And these are potential energy, kinetic energy or pressure energy. Now, these three can be interchanged, but unless energy is taken out, for example due to turbulence or lost due to friction, or energy is put in, for example you put energy in through a pump, then the total energy must be constant. Now, generally the frictional loss is negligent, and in a lot of calculations it does not take it into account because it's very, very small. However, you must consider frictional loss in certain circumstances, for example sprinkler calculations or fireground calculations when considering watering hoses. But not for all examples in Bernoulli's. Generally you can ignore frictional loss for low levels. Now, to use Bernoulli's theorem in calculations, it's essential to have all three forms of energy in the same units. So you've got to make sure that you convert whatever you're working in to the same units in the calculation. And the Systems International, the SI unit for energy is the joule. And the joule is kilograms per metre squared per second squared. However, when using Bernoulli's, the energy generally is expressed per unit mass or per unit volume. But the joule, so therefore there are actually different forms of the Bernoulli equation depending on whether you're working in joules per kilogram or joules per metre cubed. Now, in order to simplify the matter, I'm only going to use the Bernoulli equation that expresses the energy in the form of joules per metre cubed. So you've got to get all the separate energies into joules per metre cubed, which I believe is actually easier to apply in IFE examination questions. Now, let's go through the different types of energy then. What is potential energy? Well, this is the energy due to the potential above the datum line. In other words, from where you're taking the measurement from, potential energy is the energy above the datum line from which all the energies are measured. We'll come on to datum line later, but you have to select a datum line from where you're taking all the energies from across the system, and then you take the potential energy above that. Now, the potential energy per metre cubed of fluid can be considered as, here you can see rho g h, and that comes out at joules per metre cubed, where rho is the density, and the density is in kilograms per metre cubed. G is the acceleration due to gravity, which is 9.81 metres per second squared, and h is the height in metres. Now, what about the kinetic energy? Well, the kinetic energy is due to the fluid being in motion, and the kinetic energy can be considered to be half rho v squared. And again, this comes out joules per metre cubed. You understand? You've got to get it to joules per metre cubed. And in this case, where rho is the density, again, kilograms per metre cubed, and v is the velocity in metres per second. So that's the metre per second velocity. That's the kinetic energy. And then finally, the third type of energy is pressure energy. And the pressure energy is due to being under pressure. Now, the SI unit of pressure is the Pascal. But in the fire service, they use the bar or metres head. They're still used. Therefore, there's three forms of the pressure energy. And when working with this calculation, you've got to select the form of pressure energy relating to the question. So again, there's three forms. Now, to convert from a bar to a Pascal, you use the following. P times 100,000. So whatever, if it's 7 bars, that's 700,000 pascals. And again, that comes out at joules per metre cubed. To convert metres head to pascals, you use the following, which is rho GZ. Again, that comes out at joules per metre cubed, where rho is the density, again, kilograms per metre cubed. G is gravity, acceleration due to gravity, 9.81 metres per second squared, and Z is the height. So therefore, Bernoulli equation for working with these examinations, it can come in three forms, whether it's pascals, metre head or bar. When you're working in pascals, this is the formula. PA, which is the pressure energy in pascals at point A, plus rho GHA, which is the potential energy at point A, and half rho VA squared, which is the kinetic energy at point A, equals PB, which is the pressure energy at point B in pascals, plus rho GHB, which again is the potential energy at point B, plus half rho VB squared, which is the kinetic energy at point B. Do you understand? You've got the three forms of energy. The 3 at point A must equal the 3 at point B. That is quite simply what Bernoulli's formula is. You fill in these points. If the equation is in bar, you use the following formula. PA times 100,000 plus rho GHA plus half rho VA squared equals PB times 100,000. Don't forget your times in the pascals by 100,000 plus rho GHB plus half rho VB squared. The only difference is the energy, the pressure energy. In this case, it's PB times 100,000, not just PB. Now, if it's in metre head, this is the formula you need to pick up. So if it's quoted in metre head, the first thing you get is rho GZA. This is the metre head pressure at A, plus rho GHA, plus half rho VA squared equals rho GZB. In other words, the pressure energy in metres head at point B, plus rho GHB, plus half rho VB squared. Do you understand? There's only one thing that's changed in all three, depending on pascals, bar, metre head. So do you understand the fundamental principle of Bernoulli? Fluid can have three types of energy. You've got potential, pressure and kinetic energy. At any point in a system, any point on a datum line, any point along there, those three energies must be the same. In other words, A plus B plus C equals D plus E plus F. All you have to do is fill in all the known quantities in the right format, which is joules. When you've done this, you can pick out the missing energies. For example, if A is 200 joules and B is 300 joules and C is 100 joules at point A, that gives you 600 joules. Now what happens if you've got 250 joules at point D and 150 joules at E? What is the energy at F? Well, it's 600 minus 250 plus 150, 400. It gives you 200 joules. The energy at F is 200 joules. Once you've got that energy at F, you can then work out what it is, work out whether it's the height, the pressure. You can work it out, but that's how it works. Bernoulli's theorem is as simple as that. A plus B plus C equals D plus E plus F. Fill in all null values and then you find out what's missing. Now, once you've determined, like I say, the energy, you can determine, for example, the diameter of the nozzle, the pressure at the branch, etc. All you do is go working back from what you had. Now, if frictional loss is to be applied in any calculation, all you do is put the energy loss at point B. In other words, it's second in the system. In other words, if you've got frictional loss, A plus B plus C, equals D plus E plus F plus G. In other words, the frictional loss will come in the second part because you've lost the frictional loss on the way down the pipe or what have you. So if friction loss is in there, it always comes at the second point, the frictional loss, because you've lost that, making the flow going from point A to point B. Let's summarise then how to apply Bernoulli. First of all, convert all units to the SI units, Systems International. Place them in the formula. Cancel out to determine the missile energy, in other words, missing energy. In other words, if you've got A, B and C and you've got D and F, you want to work out E, cancel the rest, you'll be able to work out E. And then convert back to the original format to determine the missing parameter. Now, before we go through some model answers applying Bernoulli's, you also need to know the continuity equation. When considering Bernoulli's, it's very important to understand this continuity. And this is due to the fact that in a closed system, the rate of flow, Q, quantity of flow, which is always in metres cubed per second, don't forget you've got to get the right format, metres cubed per second, can be considered as constant. In other words, Q all the way down the system is the same in a closed system. And Q equals VA, where Q is the rate of flow in metres cubed per second, V is the velocity, metres a second, and A is the area in metres squared. So that's the continuity equation. Now, if this flow is constant, then you've got to understand this as well. If that Q is constant, then the AA, in other words, the velocity of the water or fluid at point A times the area at A must be equal to the velocity at B times the area at B. So VA AA equals VB AB. It's got to be the same. And this is shown in this diagram here. As you can see, if you reduce the velocity, or in this case here, you've reduced the area, for example here. The area at B is less than the area A. Now, if you've halved the area, you must double the velocity because the rate of flow in that pipe is the same. So if the area is halved, the velocity is doubled. So you've got to remember the continuity equation. Now, in the reverse, if water flows down at a pipe and it tapers out, in other words, the area increases, as it tapers out, what will happen to the velocity? Well, as you increase the area, the velocity will go down. If it goes back down again and it reduces the area, what happens? The velocity will go up. Don't forget, VA is constant in a closed system. Now, obviously, this is a very important relationship when attempting Bernoulli's calculations, as will be shown later. Again, before we actually carry on the calculations, I would also like to give you a few tips to make sure mistakes aren't made, because people might know the principles of Bernoulli, but when they're applying it in the examinations, they get pressured, they forget to do certain things. Now, I'm going to give you a few tips to help you. First of all, whatever information is given to you, produce a sketch and enter all the details given in the question first. It gives you a better insight into what you're actually trying to work out, and it makes you understand the problem much clearer. As you can see in here, I've put all the calculations and the information in. I've put my datum line at the lowest point of the system, where the vehicle is. You put in your water power is 4,000 watts, your rate of flow is 500 litres a minute, your diameter of your hose is 45 mil. The person's working on a branch 23 metres high and the diameter nozzle is 25 mil. Do you understand? You've got your point A where the fire engine is, you've got your point B where the fireman is. But then it gives you a clearer picture of what you're trying to work out. That's the first tip. So do a sketch. Tip 2, always convert all the units to SI units before attempting to answer the question. If it says 600 litres a minute, don't just put in 600 because people forget to convert it. Convert it. Many candidates make mistakes because they don't convert the units first. So as soon as you get a number, change it into the SI unit. Place that number in to stop you putting it in the wrong format in Bernoulli's equation. And here is a list of the most common units. Don't forget, length has got to be metres. Area, metres squared. Velocity, metres a second. Acceleration due to gravity is 9.81 metres a second squared. Height is always in metres. Metres head, which is Z, is always in metres. Energy joule, don't forget, a joule is kilograms metre squared second squared. Pressure, which is a Pascal, is newtons metre squared. And the volumetric flow, Q, is always in metres cubed per second. Again, don't forget, metres cubed per second. People get that wrong. They do it metres cubed a minute. It's meters cubed a second. They are the SI units. Convert any information given to you into those forms as soon as you can before you start applying it into Bernoulli's. That's tip 2. Tip 3. You've got to place a datum line from where you're taking all the energies from. So wherever you take it from, actually, it doesn't really matter because it will still work out, but it's got to be a straight line, a datum line. Now, if it's a horizontal pipe, always put the datum in the middle of the pipe. Why? Because the energy is zero at both points. The potential energy is zero because it's above and below. Do you see what I mean? There's no potential energy above and below is the same. So if you've got a horizontal pipe, always put the datum line in the middle of the pipe. Always put it in the middle. Now, if this is not the situation, for example, what can you do then? Well, always put the datum line at the lowest point of the system. In other words, wherever it's the pump or the branch or the nozzle always draw your sketch, and wherever the lowest point is, put your datum line. Don't put it in the middle and start doing negative energies. Don't do that. Always put the datum line at the lowest point of the system, and it makes it a lot easier to answer the question. Now, I just want to reiterate what I said earlier. This is, again, very important. People presume that Bernoulli's theorem is a very extremely complicated formula. However, don't forget it isn't. It's a simple principle. 3 energies, potential, kinetic and pressure. Whatever's at one point is always the same at another point if you ignore friction. A, B, C equals D, E, F. What do? You fill in all known entities. Fill them all in, transpose them across, you get your answer. It's as simple as that. That's the theory. Now we're going to apply it in some model questions.